不好意思，我们这场演讲应该还是会用英文进行，那所以就开始吧。So my name is 赖廷彥, and today I'm going to introduce Keelung, which is a DSL for building ZK programs. So again, I'm now working for this company called BTQ, which is founded by a group of post-quantum cryptographers. And the topic we're introducing today, Keelung, it's one of our products. So before talking about zero knowledge proofs, so have anyone heard about zero knowledge proofs before? Yeah, okay. So before talking about DKPs, which is zero knowledge proofs, we're going to talk about proofs of knowledge first. So proofs of knowledge is the kind of proof that allows you to show a verifier that you know something. And one example of proofs of knowledge is password. Because if you know your password, then you'll have access to some services, to some websites. So it's actually quite a useful thing. It's something that we're using every day. But the problem is that in order to prove that you know something, sometimes you'll have to reveal information about this knowledge. So for example, when you're logging into a website, you will have to show the website your password so that you can log in. And this can be pretty problematic because if this password got leaked, then someone else who also possess the knowledge of this password may also access your account. So another way of addressing this issue is by using something called a zero knowledge proof. So it's basically a proof of knowledge, but it allows you to show a verifier that you know something without revealing any information. So this is what ZKP is for. And this may sound like an impossible thing to do, but here's a classical example. So let's suppose there's a cave with two entrances, entrance A and entrance B, and there is this girl, Alice, who is trying to show the verifier, which is Bob, that she knows that there's a back door between these two caves and she can get through the back door. But she doesn't want to let Bob know that how she got around this cave. So one way to prove to Bob that she knows how to get around this cave is by simply entering from the entrance A and then exiting from entrance B. So by showing Bob that she can get around that back door, and she can prove to Bob that she possesses this knowledge. So this is one classical example of zero knowledge proofs. And ZKPs are particularly useful in boosting privacy because it allows you to prove that you know something without revealing it. So let's suppose you want to prove that you're someone, then you can, if you have the ZKP of that, then you can prove it without revealing those information. And another example is in cryptocurrency transactions. So you probably know that all of the transactions on the chain, on blockchain, it's all public. And everyone can verify it, can reveal it, but let's say if you want to make a transaction, but you don't want to disclose like the recipient or the amount of money you want to transfer, then you can make a ZKP to prove that you have done this transaction without revealing those information. And it's also pretty useful in other scenarios like voting, because when when you're voting, you don't want to show to anyone that who you're voting for. But you also want to verify that your vote is in the ballot box when they're counting your votes. So this is another useful case of VKP. There are other applications of VKPs. And many of these VKPs, they're constructing using some sort of circuits or model. Okay. And these circuits, they're often formulated with a bunch of polynomial equations or gates. And examples include this R1CS, and another one is called AIR. And today we'll be mostly using this R1CS as our examples because this is the protocol that Keelung is targeting. So let's take R1CS for example. It's composed of tons of constraints that looks like this. So this is one constraint, and each of these constraints, they contain tons of variables. And these variables are arranged in such a way that it's an equation between the product of two polynomials and another polynomial. So this is what a typical R1CS constraint looks like. Yes?
But do you have the modulus or something, because xn, if you multiply them, there should be the xn of like x power of 2n, like something like that.
Oh, this is a linear combination of these variables. So that's its constraint. So it's comprised of 3 linear polynomials. So all of these variables, they don't have power to the other. Yeah. So does that answer your question?
Probably.
Yeah, we'll look at other examples. Okay, so in order to formulate the VKP, you have to generate a lot of this kind of constraints. But they're almost impossible to construct by hand when the statement you're trying to prove is a bit complicated.
I'm not sure what's the knowledge or what's to be proved here in this format.
Oh, this is just a generic form of the constraint, so it's just.
So there's no running example to this.
Yeah, not in this particular.
For example, the parameters or
okay.
values of the x's.
I see. Maybe we will look at other examples, a more concrete example. Yeah, this is just a generic form of the constraint. Okay. So what I'm trying to say is it's impossible to construct by hand. So that's why we need a programming language for formulating these statements and a compiler for doing this kind of translation. So let's talk about domain-specific languages, or DSLs. So apparently we need a language for constructing ZKPs in order to provide a high-level, more intuitive way to describe ZKP computation. And also because it's really easy to break your constraints when you're constructing it by hand. So if we have a language, then it will be easier for the non-experts to work with ZKPs. And it also abstract away the details of the underlying protocols, such as R1CS or AIR, because sometimes you may want to change to another protocol for some reason. But the problem is not any programming language will do. So language for describing ZKP will typically have to support an arbitrary precision arithmetic. such as nomenclature of arbitrary length. Yeah. Also, do you have any questions or?
Yeah, you don't need arbitrary precision, right? You just need enough to express the finite field that your curve that your polynomial is expressed over.
Yeah, but sometimes the number will be larger than that field, so you may need like 5 field elements in order to express this kind of really big numbers. So you will want your language to support this kind of data type. Yeah, that's a really good question. And also, the language you're using will have to prohibit infinite loops, because when we're constructing EKPs, we're actually we're synthesizing a circuit. And if your program have infinite loops, that means the circuit you're constructing is of infinite size. And you certainly don't want that to happen. So the language you're using will have to discourage people from, yeah.
Can you express arbitrary totality?
Sorry, arbitrary what?
Totality. So programs that are known to terminate in a fixed number of steps that might be very large.
Yeah. So I think I'm going to show you how to do this, yeah, in our language. Yeah, because it's really difficult for something to stop. If you have program in some languages like ECTA, which requires every program to be terminating, yeah, it's really difficult. So our language will have to terminate if you're constructing this EKP. And instead of describing a one-way computation, which is what most programming languages do, it will need to describe a relation rather than a one-way computation.
So what is the relation?
So let's say a typical C function, you may have 3 inputs and 1 output. And in order to get this output, you will need all of these 3 inputs. And so this computation is one way. And so you cannot revert going from the output back to the input and etc. Yeah. So the language itself, it doesn't describe this kind of one-way computation, but rather the relation between all of the inputs and outputs. Yeah. So there's no direction.
Yeah. I think. Do you mean that in relation, one input is allowed to be mapped to more than one output?
I'm sorry, can you say that?
In relation, typically when we talk about relation, we mean that an input is allowed to be mapped to more than one output. Is that what you,
yeah.
As opposed to a function where one input is mapped to only one output. So is that allowed in your language?
So in this language, Keelung, there is really no difference between input and output. Everything is input. So imagine you have a circuit with lots of pins sticking out, and what your language or what you do when constructing the EKP is we try to express the constraint, the relation between these inputs. So there's really no inputs or outputs. Yeah.
So for termination, what sort of relations can be placed on the input to guarantee termination? So for some functions, you might be able to express it simply by saying if the input is n, then there's a recursion with depth n, or something linear like that. But for other more complex functions, are you able to express those as well?
I think our language is not that expressive. So, for example, we can't even do induction on those inputs. Yeah. Yeah. So I show you that our language is embedded in Haskell. So there is a phase called elaboration, that's when the Haskell part is moving. So by infinite loops, I mean it's we will not allow this kind of loop to happen after elaboration. So after elaboration, what we get is concrete data. It's not there are no moving parts, so there are no loops or whatsoever. Yeah.
Okay, thank you.
Yeah. So most general purpose programming language won't do, and that's why we need a DSL for constructing UJP. And there are already other existing DSLs for constructing UJPs, such as Circom, Ducatis, Catalog, and more. But some of the languages like Circom, if you have tried them before, you found out they're really low level. So you have to take care of a lot of the details yourself, and it's pretty inconvenient to use. And so that is one of the reasons why we want to build Keelung. And another thing about these DSLs is that they're all standalone DSLs. So that means they have their own ecosystem, tooling, syntax highlighting, and all those stuff. So you're essentially learning a new language when you're trying to learn one of these DSLs.
Sorry, what language does this DSL use to build it?
Oh, so you mean Keelung, our language?
This for?
Oh, I think all of them, they are implemented in Rust right now. So, yeah.
Socrates in Python.
Oh, sorry, which one?
Socrates in Python, isn't it?
But
I believe he has a Rust implementation.
Ah, right, okay.
yeah. I think Circom was using JavaScript before, but they're not all moving to Rust.
But they still have JavaScript interface based on Rust.
Yeah, so besides from the language, we also need a compiler for doing this kind of translation from the language to low-level circuits. And also, because those constraints generated by hand, they may be redundant. So you may want to reduce the size of constraints because it will make the proof size smaller and easier to verify. Yeah, so if you have a compiler, then the compiler can try to optimize your circuit for you. So that's why we're building Keelung. And so Keelung is a ZKP DSL embedded in Haskell. That means that when you're writing Keelung, you're actually writing Haskell. So if you already know how to write Haskell, then there will be no difficulties in writing Keelung. And it also comes with a compiler that is also written in Haskell. And it's based on a paper called Snowcall by Gordon Stewart. So we have, so the language Keelung itself is based on this academic piece, but we have written all of the code. Yeah, and we have recently just open sourced it under the Apache 2.0 license. So everyone is, if you have run into any issues or want to contribute, please do. Yeah. So this is the repository, and so one reason why we embed Keelung in Haskell is because it's an excellent language for embedded DSLs. And another thing is that we want to use Haskell's type system to help us enforce those invariants we need when constructing ZKP. And another thing, really special thing about Haskell is that it allows you to have fine control over which kind of side effects you want in your DSL. So that's why we choose Haskell. And by embedding Keelung in Haskell, we can also get free stuff like IDE, syntax highlighting, and all that good stuff. And it also have a package manager, so we don't have to to the event text manager like what the practice they do. And it also comes with a lot of documentation tutorials so that we don't have to write them ourselves. And so overall, it's a nice language to embed into. And another reason why we choose Haskell is because all of the ZKP DSLs we just saw, they're all standalone. So their user base is quite fragmented. And so by embedding Keelung into Haskell, we think that there should be more people who know how to write Haskell than all of those DSLs combined. Yeah. And this is the overview of our compiler. So what it does is it transforms the syntax trees constructed when you are writing your Keelung program, and it goes through passes of rewriting, and after compilation it becomes a bunch of constraints, like the one you see in the previous page. So it becomes thousands of constraints, and then we will pass those constraints to optimizers so that we can reduce the size. So that's a high-level overview of our compiler, but we will now look into the details of the internals of the compiler. So today we will only be talking about the language itself. Okay. So far, do you have any questions? So feel free to interrupt me. So if there's no questions, then I'll move on to introduce the language itself. So since it's embedded in Haskell, it inherited all the language features of Haskell, such as functions and module systems. And so we only need to maintain a really small core language for describing the building blocks of different construction ZKPs. And Keelung, it also have a simple interface for bridging your Keelung program and the Haskell outer world. So let's look into what the core language is like. So right now it has 3 primitive data types, and the most primitive one is it's a field element, and that's because the protocol we're using, they're often constructed some finite fields. So the most primitive data type is a field element. And we also have booleans, but they're basically just field elements in disguise. And all of these booleans, they come with a constraint that says this field element is either 0 or either 1. So let's look at a more concrete example of what this constraint may look like. So let's suppose we have a variable b, which represents a field element. Then in order to make this field element either 0 or 1, we can add a constraint like this. So only 2 elements are allowed if this constraint is there. So this is one of the most simple RCS constraint. So does that answer your question?
So what's the knowledge here?
Knowledge is that b is either 0 or 1, because if it's 2, then this equation doesn't hold.
Now you haven't written any Keelung code.
Okay. We'll look at other examples.
So you'll compile those code into that kind of constraints.
Yeah.
Okay.
So we have field elements, we have booleans, and we also have assigned integers. So they're also basically just field elements, but coupled with binary representation. So let's suppose we have a number 5 that we want to represent as a assigned integer. Then let's add a constraint that requires b to be 5. And we can also add another set of constraints that says so x and y and z, they're all boolean, so we'll have this kind of so with these constraints, we now know that these are bits, and by adding this constraint, we have limited the range of this number. So this number is essentially a 3-bit assigned integer, so it can only range from 0 to 7. And it's really useful when you want to do things like comparison, because there's really no comparison field elements. All numbers, they are all equal. There's no such a thing as a larger number if you're talking about field elements. So by expressing a field element as some kind of assigned integer, we can do this kind of comparison because we know what it looks like. Yeah. So these are the 3 primitive data types that we have in Keelung. And because we are now at a functional programming language meetup, so I'm free to put this monad word on the slides. So it also comes with a monad or a context for keeping track of constraints of variables, and also we have a fake heap memory. Yeah. And so let's look at the first Keelung program. So what this program does is that it takes a public input and returns its successor. So let's look at real code. So this is what it looks like. And because ZKP is like a circuit, so you will need to specify how many inputs you want, how many pins you have in your circuit, and also what kind of type that pin is. So, and also this is public or private, so this is a ZK pin. So once we have specified that we want input, and then we can bind it to a variable x, and then we can do a bunch of mathematics and stuff like that. So this x, it has type field, and we're actually overloading all of these literals and these operators. They're all like this. Take this one for example, it's a field element. So in Haskell, the language allows you to express a field element like this. And also you can do addition or multiplication like you would in other data types like an integer. So this is what the successor function looks like. Now let's try to compile. So for compiling it, let's elaborate it. So when we do elaboration on a Keelung program, what it does is it executes all of the Haskell moving parts. So, and in the end, we get a pure concrete data structure that represents the relation between the inputs and the outputs. So in this example, we have a circuit that takes a field number input and it outputs its successor. So this is what it looks like when elaborating a Keelung program. And let's try to compile it into constraints. So now we have one CS constraint, and it looks like this. So it has two variables, and we're using this $0 as the output variable and the $1 as the input. So now it has a constraint like this. So any questions or yeah, please.
I noticed you're compiling to GF181. Can you do arbitrary finite fields?
Oh,
What kind of fields can you use?
we used to be able to do arbitrary finite field, but then we cannot. But recently I found that maybe we can do that again, so we don't have to. Yeah, so we will still have to specify what kind of field we're working on, but I think we can make it arbitrary. But for now, it's hard-coded, yeah. Okay, let's move on to other examples. So instead of adding just one, we can make it more general by making it a Haskell function. So in this case, at n, it takes an input that and field element n, and then adds it to the input. So what we're looking at is it's actually not a Keelung function because there's no such a thing as function in Keelung. And so this is actually a Haskell program. And in order to compile it, you will have to apply all of the arguments until you get a final stuff like this comp field. So it actually allows us to achieve meta programming in Keelung by using features like functions in Haskell. So let's try to elaborate this function. Want to do that, we will say that it doesn't know how to do this because it's not a Keelung program. So in order to make it a Keelung program, we will have to apply the concrete field number after 13, and then we can get a concrete Keelung program. Yeah. So then we can continue to compile it or interpret it. Yeah, let's try to do that. So Keelung comes with a command called interpret, which allows you to drive all your Keelung program, see what it looks like to run it. So in this example, we're feeding public input, which is 1, and in the end we'll get a 4. Yeah. So with Haskell functions, we can instantiate multiple instances of the Keelung program, and we use them everywhere. Yeah, and another thing that about infinite loops is that you can also construct an infinite loop in Keelung, but you will only get a Haskell program that doesn't terminate. You won't get the final Keelung program because your program it simply doesn't terminate and elaborate. Yeah. So you only get a Keelung program if the Haskell program terminates. So in this example, we're mapping over a list of field elements and apply all of them to that one. So in the end, we will get Keelung program that outputs a list of fields. And let's give that a more interesting example, which is conditional. So in this example, it takes a field element x to see if it equals 42, and if that's true, then we will return 100, else 0. So that's we try to elaborate it, we will get an expression. So this is what it looks like when we elaborate it. But if we try to compile it, let's modify these examples to make it more dynamic program. This program, it has one input variable, which is $1, and we have 3 constraints. So the first constraint says that so yeah, I'm now a bit too drunk to explain this constraint. But as you can see, yeah, okay. So it's probably, you probably don't want to write this kind of constraint by hand, especially when you're drunk. So yeah, so if you look really hard at it, you should figure out why this program computes the result that you want. Okay, so let's get back to the slides. So like I said, we have assigned integers. And with assigned integers, we can do all of those logical bitwise operations, like masking an assigned integer with another assigned integer, that kind of stuff. And in this example, we can see that we actually have a number in the type of this program. And we can do this because Haskell, to some extent, supports dependent type. So we can actually annotate the bit width of a number to the type. And another benefit of annotating this bit width in the type is that we can prevent users from mixing all of these assigned integers up, because it's really easy to do that if you're writing, if you're using other languages like, so I can't think of any examples, but you get the idea. So we can establish kind of type error here. Yeah. So that is pretty much all about those primitive data types, and now let's look at assertions. So because constructing ZKB is all about enforcing constraints on those variables. So assertion is probably the most important thing we want to do when constructing ZKB. So in this example, we're asking for 2 inputs, and we're stating that the first input should equal to the second plus 3. So let's try to have this example. So it also generates a bunch of constraints, but so I think we will now look into this kind of constraints, and it's a bit complicated because of this quality operator. It's an operator that allows you to compute the result in a decidable manner. That means it really produces another value that is either 1 or 0. And it's actually kind of difficult to do in models like R1CS because all you get is a bunch of numbers with addition, subtraction, multiplication, things like that. So you have to think up a way to make this output happen. Yeah.
I don't see an assert in this example.
Oh, oops, that's making an assertion. Okay, that looks better. Let's try to compile it and see if anything changes. Oh, this is, yeah. I think this is the correct example that I want to show you.
Okay.
Because this is a lot simpler. So it takes 2 inputs and it simply scales out and it should add up to 0 like this. So, yeah, thank you. Okay, let's move on to other assertions. So another kind of assertion we can do in Keelung is the relation between. Anyway, we can perform division or modular unsigned integers, and we can do this by asserting that this kind of relation holds. So if we multiply the divisor with portion and add it with the remainder, we should get the dividend. Yeah, okay. And another thing I think is interesting about this example is that because Keelung is not describing a one-way computation, it's actually describing the relation between two variables, so we can actually do this kind of stuff. So what this program do is it asserts that there exists a certain portion such that when you multiply it by 2, you get the dividend. So we're actually kind of working the other way around rather than having that kind of one-way computation. Yeah, so we can do this. We can describe this kind of relation in Keelung, and the compiler will try to find a way to satisfy all these constraints when working on linear generation. So have you heard of languages like Prolog or logic programming? Yeah, logic programming. So if you have programming this kind of language, you'll find that there's also its computation is also not one way. You can dig a hole somewhere, and if it has enough information, you will try to derive the result for you. So it's kind of interesting. So Keelung is a lot like Prolog in this sense. You can dig hole somewhere, and the compiler will try to satisfy the constraint. Yeah. And also Keelung we have mutable arrays, but since we are now at the functional programming, you're probably not too interested in this topic because we all know how to program without multiple arrays. But we add them to Keelung nonetheless because there are still a lot of developers who are more familiar with this kind of thing, multiple arrays, and also a lot of algorithms they're also described in this manner. Iterative manner, so it helps to broad rate our language. Oh, please.
Yeah, I have a question. To get mutable arrays, do you end up packing up all of the fields of the array into like a single field element or multiple field elements? Because that's what I have done before.
We would want to do that when possible, but probably not. Yeah.
Okay, so you don't have like a transformation. So then, how do you represent it? Do you just represent each element of the array as a separate field element?
Yeah.
Okay.
Yeah. And back then when Keelung doesn't have unsigned integers, so let's go back to this example. So back then we don't have unsigned integers in Keelung, so what we can do is we use these field elements and produce them, treat them like bits. And so we'll end up with tons of constraints when we're trying to say add those unsigned integers together because they're not really designed to do this kind of stuff. So later we found that all the other DKP languages, they have this kind of unsigned integers and they can pack these field elements, these bits into a more compressed format. So we ended up like that. We also have the unsigned integers. So we would like to do that kind of optimization, in Keelung.
Yeah, I'd be glad to discuss it with you. I think we want something similar.
Okay. Okay. So finally, we also have an interface between Keelung and Haskell. So if you have know something about Haskell, you probably know that Haskell has this thing called type class. And type class allows you to describe an interface. And so in our case, if developers they know how to encode their data type into Keelung objects, then they can use it in Keelung code. Compiler will try to figure out how to compile it into Keelung objects. Okay. So about tooling, we have a language and we have a compiler, and we also have an interpreter for developing to test their programs and for witness generation. And our colleagues, they're working on prover and verify so that we can feed the constraints we just saw into a prover so that we can really generate ZK proof. And we also have a verifying this proof. Another thing is that we now have a GitHub code space, so we have a documentation for this. So if you're interested in trying Keelung out, you should be able to do this within like 3 minutes because they have a really nice playground for Keelung. So that's pretty much all about Keelung, and we'll talk about something about the future of Keelung. So the unsigned integer we have in Keelung right now actually doesn't support arbitrary long bit width. So it can only support unsigned integers if the bit width is within the range of the underlying field. And we would like to extend that. So that is for arbitrary long. And also we don't have comparison operator on unsigned integers yet, so we want to add that to the language. And we also want to add some more robust compilation and test optimization. It would be nice if we have more libraries, especially cryptography community, so that people who want to implement their stuff, they have these building blocks to work. And also maybe some libraries for the PID standards. And also people are starting to put ZK and AI together. I don't know how, but they're kind of starting. So if you're interested in this and you want to write some Keelung, you can help us with these libraries. And in PDQ, the company we're working for, we also have a team that is working on hardware acceleration, hardware for generating those ZK proofs. So it would be nice if we can compile our Keelung code into something that hardware can accept, and so we can design some kind of specialized optimization for big hardware. And the constraint that I kept showing you is in the format of R1CS, but that's not the only ZK SDK protocol available. There's actually other protocols like Plug or Polytools, and we would like to support more of these proving systems. Yeah, and so we're now working with organization and initiative that is trying to bridge the gap between languages and proving systems. So what they want to do is have some kind of intermediary, some IR in the middle, so that instead of compiling everything down to all of these different proving system, constraint system yourself, you can just compile them to declare, and then they'll try to pick it up from there and compile it and optimize them into the constraint system. Yeah, so that's pretty much all about Keelung. Thank you. And this is our Discord channels. So if you want to contribute or have some fun, then feel free to join in. And this is our GitHub repository. So thank you. So if you have any questions or yeah, please.
Would Keelung ever need a trusted setup? Or is the setup always transparent?
It depends on the proving system you're targeting. So if the proving system you're targeting requires a trusted setup, then you will need a trusted setup. Yeah, so in some ways, not really related to Keelung, but currently the prover and the verifier we're targeting doesn't require this kind of trusted setup. Yeah.
Is it possible to build a transpiler circle to Keelung?
I think maybe it will be easier the other way around because SOCOM it's more low level, so it's probably easier to transpile something from a high level language to a lower level language because you have more information to work with, types, or that kind of stuff.
I think in that direction because maybe we can reuse the existing SOCOM libraries, so we don't have to read all logic.
Yeah, there are lots of things written in SOCOM, and it will be really nice if we can transpile them into Keelung automatically.
So there's actually a project called this organization called OpenZL. So their motive is to provide also use this slide. Their motive is to provide an intermediate representation for other languages such as circular properties. So the shared libraries that you mentioned could be done in this way, that they all compile to declare their intermediate representation. So we were also investigating in how to compile Keelung to declare. But if that's possible, then we can share some libraries between all these languages.
So for your current backend, the Aurora proving system, what does the proof size and verifications mean? What does it perform?
I'm actually not sure about the specific numbers.
So right now, all our experiments are done on top of the Aurora proving system, which it takes our CSS input, but the kind of the proving system itself doesn't rely on any elliptic curve. So it's purely based on symmetric image. So therefore, when it comes to proof size, far from ideal. Let's put it this way. It tends to be at least one order of magnitude larger than the proof size you can get from say pairing based like Growth 16, DK-SMART, proving systems that are based on whose security assumptions are based on this elliptic curve like pairing.
Then why choose that commercial?
Well, I guess we're a startup. We dedicated ourselves on research and developing post-quantum crypto primitives. So anything that cannot survive the attack from large quantum computers, we will not. Well, it's not in our immediate romance, and therefore, elliptic curve pairing is kind of out of the question.
So your performance goals are very different from the current EVM teams.
Yes. Well, I guess there's always a trade-off. So when we're thinking more of a long-term we have a longer-term plan. Well, Keelung itself, I would like to add that it's a kind of because it's a compiler, right? So it outputs RNCS, so you can bring that to any proving system, including a parent-based proving system. As long as it takes RNCS as input, you can probably hopefully benefit from using Keelung. Yeah, so you're definitely welcome to try it out.
Obvious question, why is it called Keelung?
Who came up with the technique?
Really?
Yeah.
Does he even know the city?
No. he knows, but he has never been there.
Okay.
So there's a Keelung Road, I guess.
And it's basically we need to solve this internally.
Yeah, we have to ask him.
I thought you guys did. No. I mean, okay.
So it's still a mystery.
Yes, it is.
So you mentioned earlier that you're doing an elaboration of syntax.
Mm-hmm.
What does the elaboration phase do?
It execute all of the Haskell moving parts, so functions and loops, all that kind of stuff get expanded, get unrolled. So what you get in the end is a data structure that contains a lot of syntax trees, basically. So those expressions, they are kept inside that data structure. And because we allow users to make assertions between variables, so these assertions, they also kept in that elaborated data structure. Yeah. Does that answer your question?
Yes.
Okay, if there's no more questions, then thank you.
Thank you.